If we want to represent a number in binary, say we want the number 5, then we can represent that as 101. That's straightforward enough. We have a 1 in the 1's place, 0 in the 2's place, and a 1 in the 4's place. So 4 plus 1 is 5. But how do we represent negative 5? Well, negative 5, of course, is just negative 101. But the problem we have is there's no such thing as a negative symbol inside the computer. We only have 1s and 0s. We could decide that a 1 represents negative numbers and always put a 1 in the most significant place if it is a negative number. So 1101 would then be negative 5. We would then, of course, have 0 as positive, and 0101 would be positive 5. Now that's nice and convenient. We can detect whether something's negative or not, and it's very easy for us to read off the number 5 here because 101 is 5 in both the positive and the negative case. Now that's easy for humans, but there are some issues with this approach. One of the issues is that how do we represent the number 0? Well, 0, of course, is 000, but do we put a 1 or a 0 in front? Well, actually, we can put a 1 or a 0 in front. So all zeros, that would be 0. But we also have 1, 0, 0, 0. So we have two versions of 0. Now, inside of the computer, this can create complexities. It is going to require more complex hardware in order to handle the fact that there are two implementations of 0. And of course, positive and negative makes no sense in the case of 0. We also have the problem that adding and subtracting would be different operations, and we would need more complex hardware to do the subtraction. The solution that is typically used inside of a computer is what we call 2's complement. And if we have a look here at the number wheel, we can see how the 2's complement numbers are arranged. We have 0 at the top, and then the positive numbers increasing down the right-hand side, and we have the negative numbers decreasing down the left-hand side. Notice that at the bottom, the number that used to be negative 0 in our example up here is in fact negative 8. So we have from 0 to 7, 7 being the maximum positive number we can get, and minus 8, negative 8 being the most negative number that we can get. But this isn't as straightforward to understand. For example, if we look at our example of 5, which was the positive version of it was 0101. If we come across the circle here to negative 5, we have 1011. And our 011 doesn't look anything like 101. So how do we convert from one to the other? Well, what we're wanting to do is actually multiply by minus 1. So we need to find some way to multiply by minus 1 in order to go from positive 5 to negative 5, or from negative 5 across to positive 5. We can try and solve this by observing a couple of things. First of all, if we divide this up so that we have non-negative numbers on one side and negative numbers on the other side, if we have a look at what happens when we reflect around this line or over this line, if we take a number to the left, in this example, negative 1 is 1111. If we invert those bits, we jump to the other side, which is all zeros. If we take our 110 here and we jump to the other side, we get 0001. And we can do that anywhere. Back to our minus 5, our negative 5 example here, 1011. Reflecting that over, crossing this line, we actually get to positive 4, which is 0100. So notice that these two numbers are the inverse of each other. The 1s become zeros and the 0 becomes a 1. So we can say that by inverting the bits, we will cross this red line. We can also say that by adding 1 to any of these numbers and ignoring the fact that they are 2's complement numbers, we will always move in a clockwise direction. So plus 1 will always move us one step this way. Even over here, notice that 1101, if we just treat this the same as we do non-negative numbers, then plus 1 would be 1101, and that's exactly what we get up here. So a plus 1 here also takes us in a clockwise direction. So with this understanding of reflecting across the line and moving plus 1, we can find a way to jump from one side to the other. So for example, if we want to multiply positive 5 here by minus 1, means that we want to get over here. So if we take our positive 5 and we invert the bit, so 0, 1, 0, 1, inverting the bits becomes 1, 0, 1, 0. So inverting the bits will take us across to here. And then if we add 1, we will get to negative 5. So this is our invert, and this is our plus 1. So by inverting and adding 1, we've managed to get from positive 5 to negative 5. If we go the other way, so we have our 1, 0, 1, 1, and we reflect to the other side, across the red line, we will end up at positive 4, and then if we add 1, we will end up at positive 5. So it works in both directions. So the rule that you need to remember is we invert and add 1, and that is equivalent to multiply by minus 1. And we can use this to figure out 2's complement for any number by starting with its positive number. So let's take another example. I want to know what negative 3 is. I start with 3, 0, 0, 1, 1, 0, 0, 1, 1. I'll invert the bits, and then I'll add 1. So 1, 1, 0, 1 in 2's complement is negative 3. And if we have a look here, negative 3, 1, 1, 0, 1, we can see that that agrees with our layout on the number wheel. And so 2's complement removes the problems that we had up here. We no longer have two versions of 0. 0 is simply 0. And positive 5 stays the same. It's still 0, 1, 0, 1. And negative 5 now, though, has changed to 1, 0, 1, 1. It's not as easy for us as humans to read, but this is actually much more useful for the computer. One nice side effect of this is that subtracting numbers now simply becomes the same as adding numbers. We just need to multiply the second number by minus 1. For example, let's say we want to do 5 minus 4. This would be the same, of course, as 5 plus negative 4. We already know how to add binary numbers, and now we know how to multiply by minus 1 to get our negative 4. So let's perform this operation. We'll start with our 5, which was just 0101, and we want to add negative 4. Positive 4 in binary is just 1, 0, 0, or we're dealing with 4-bit binary here, so it's 0, 1, 0, 0. To multiply that by minus 1, we need to invert the bits. So that becomes 1, 0, 1, 1. And then we need to add 1. And now we can perform the addition in the same way that we previously did. We just do 1 plus 0, 0 plus 0, 1 plus 1, which gives us a carry, and then 1 plus 0 plus 1, which gives us 1, 0. So we have an extra bit here. Our result has to be 4 bits, and so we are going to lose this leftmost bit. But notice that the number is actually still correct, 0001, which is just positive 1, and that is the answer. 5 minus 4 is positive 1. So long as these two numbers are both positive, whenever we do a subtraction, we will stay within our range, because the biggest that we can do is 7 minus 7, which will just bring us back to 0, or 0 minus 7, which will bring us down to negative 7. And so we can't leave this space by performing this operation. However, if we started with a negative number here, we could possibly drop off the end and wrap around over to here and get an incorrect solution. So that is something to watch out for. But when we're adding numbers in a limited number of bits, that's always a problem, with or without negative and with or without subtraction. So we've been able to perform an operation that our computer can already do. Our computer can already add. And so just by adding this multiply by minus 1 operation, we've been able to produce an add. So this allows us to subtract numbers more easily inside of the computer, even though it's more complex for humans to understand. And inverting numbers is a very simple thing for us to implement in hardware. All we have to implement is the invert operation, and that's just bitwise inverting all of the bits. We can use a NOT gate for that, and we'll see that adding 1 with existing adder hardware, we can just use the carry in, is also very easy. So this is a very cheap to implement subtract if we already have add. And that's what I plan to do next. I plan to build an arithmetic and logic unit that can add and subtract, and this will be the starting point of our RISC-V CPU.